Hello everyone, I'm Wu Siyuan from University of Macau. In this video, I will introduce our work, K-best egalitarian stable marriages for task assignment. Task assignment has many applications in real world, such as delivering and transportation, special crowdsourcing systems, online dating. These applications usually have requirements from agents on two different parties. For example, in special crowdsourcing systems, workers consider distance, and tasks require working skills. The stable manager problem is a classical problem that finds an assignment considering the preference of agents in a two-sided market. Use marriage as the example. We have males and females, and we have the full preference lists from each agent to all agents on the other side. The position of female 1 in the preference list of male 1 can be regarded as the dissatisfaction of male 1. A stable marriage is a stable perfect matching. It has undisjoint male and female pairs. If M and W prefer each other than their partners, they have the motivation to break this matching. A stable marriage doesn't have this kind of blocking pairs to guarantee the stability of the assignment. How to find a stable marriage? A classical algorithm deferred acceptance algorithm is a sequence of proposal and accept or reject actions. If males propose and females decide to accept or reject, we can get the male optimal stable marriage. It achieves the best choice for each male and the worst choice for each female. Obviously, it's not fair for females. And if we switch the active side on females, we can get the female optimal stable marriage. It's not fair for males. The deferred acceptance algorithm can find the single-side optimal solutions in Owen square time. It's fast, but not fair. To ensure fairness, the egalitarian stable marriage problem is to find a stable marriage that minimizes the egalitarian cost. The dissatisfaction of an agent is represented by the partner's position. The egalitarian cost is the cumulative dissatisfaction. For example, in this matching, females get the third, second, third choice, and males get the first, second, first choice. We have to minimize the accumulated dissatisfaction of all agents to ensure fairness on two sides and get a stable marriage with quality. To help assignment process for decision makers, we aim to provide a set of high-quality stable marriages. Our problem is to find the K-best stable marriages in terms of egalitarian cost. We prove that this problem is an NP-hard problem, and from the view of real applications, the name of agents increase in the large-scale data. Even the N is small, counting all stable marriages is a sharp P problem. The number of all stable marriages can increase in exponential size. It suffers from the extremely large search space. Let's use a toy example to explain the structure of stable marriages and the search space. By deferred acceptance algorithm, we can have the male optimal stable marriage and the female optimal stable marriage. Other stable marriages appear in the gray area in the preference list. Continue to apply deferred acceptance algorithm showing with blue color, we can recouple some pairs and get a new stable marriage. Rotation is a compact structure of this recoupling process. Rotation is an ordered sublist of pairs. How to recouple pairs with rotation structure? Each male is reassigned with male in the next pair. This process is also called rotation elimination. We also can calculate the dissatisfaction difference caused by eliminating a rotation. The all-stable marriages can be represented by a rotation poset, which is a DAT. We show the pairs in rotation 1, rotation 2, and rotation 4 here. The partial order in the rotation poset means if we want to find the rotation 4 in the assignment, we have to eliminate rotation 1 and rotation 2 first. Otherwise, we cannot find pairs in rotation 4. Based on rotation poset, each stable marriage can be generated by a set of rotations. Because of the partial order, they should be closed under all predecessors. For example, we can eliminate rotation 1, rotation 2, rotation 4 to generate stable marriage 1. Another example is eliminating rotation 1 to rotation 5 to generate stable marriage 2. The terminate nodes highlight with blue in the rotation graph. They are antichain to the corresponding closed subset. The antichains, closed subsets, and the stable marriages, they have a one-to-one correspondence by graph search and rotation elimination. Our problem is to find the k-best solutions. Before this, how to find the best solution? With the structure of all stable marriages, now we don't have to scan all the pairs in the assignment to calculate the egalitarian cost. For example, eliminating rotation 1 to rotation 5, the egalitarian cost of the corresponding stable marriage is the egalitarian cost of the male optimal stable marriage minus the dissatisfaction difference caused by rotations in this closed subset. To find the top one result, the egalitarian stable marriage problem is transformed to find the maximum weight closed subset. It can be solved by a network flow-based algorithm. Apply min-cut algorithm on the rotation graph. We can find the best result. But min-cut algorithm cannot find the top two results. To find the k-best results, the solution is to find the k-best closed subset. The Bluetooth solution is to enumerate all the closed subsets. This method is inefficient. Our solution is to using pruning techniques to reduce the search space. We study layer bound and the rotation bound to pruning the unpromising closed subset. The solution for the egalitarian stable marriage is to apply min-cut algorithm on the rotation graph to find the best closed subset globally. The layer bound is to apply min-cut algorithm on the subgraph to find the best closed subset on the subgraph. Each time we remove an outlier. The example here, we can apply min-cut algorithm on the layer 4 subgraph, and we can find the best result on the layer 4 subgraph. This is the layer bound of layer 4 subgraph. Each time we remove an outlier, after that we can get the layer 3 subgraph. How to search with layer subgraph? With layer bounds. First, we start the search. We find the closed subsets from right, and in this searched area, we have some candidate top K results on the hand. After that, we compare the layer bound with the case candidate result. If we cannot find a better result on the layer subgraph, we stop. Otherwise, we continue to search. The second bound is the rotation bound. The rotation bound is try to find the possible best result of the closed subsets corresponding to all antigens consist of a rotation R. Here we use rotation 6 as the example. Any closed subset cannot be larger than the sum of all positive rotations. After that, rotation 6 itself should be in it. By the definition of the closed subset, the predecessors of rotation 6 should be in it. And by the definition of the antigen, the successors of the rotation 6 cannot be in it. We tied the rotation bond, and we can put in the corresponding closed subsets. With the layer bound and the rotation bound, we can efficiently search the search space, and we evaluate our algorithms on the synthetic datasets and real datasets. We compare the response time and the number of enumerate stable marriages. With the increase of the input size, we can achieve a better time performance. And the K here is not sensitive because the K is more smaller than the number of all the stable marriages. And the layer bound can stop at the middle layer. Most of rotations can be pruned eventually. The time cost of two bonds are acceptable. Apart from the improvement of the efficiency, we also can provide the reassigned pairs to decision maker by the rotation structure for the further analyze. In conclusion, we provide a set of high-quality stable matchings in terms of the egalitarian cost to ensure fairness. We propose efficient algorithms, use pruning techniques with layer bound and rotation bound. We evaluate our algorithms on the real dataset to demonstrate the performance. That's all. Thank you.